Okay, this screencast is going to talk about liquid crystals. Some of the objectives for this screencast are to describe the meaning of the term liquid crystal, distinguish between thermotropic and lyotropic liquid crystals, describe the liquid crystal state in terms of the arrangements of the molecules and explain thermotropic behavior, outline the principles of the liquid crystal display device, and discuss the properties needed for a substance to be used in liquid crystal displays. So these are the things that you should be looking to understand as we move through this screencast. Okay, so what is a liquid crystal? It is a substance that flows like a liquid, but it has some order to its molecules. So it can be viewed as being somewhere between a liquid and a solid. So it is a phase of matter that can move like a liquid, but it does have order to its molecules. The molecules themselves must be rod-shaped, and we'll look at the structures that contribute to rod-shaped molecules, and they have to be aligned in the same direction when they are in the liquid crystal state. One of these states is called a nematic state. There are other types: smectic, cholesteric, and columnar. And I don't know if I say those right or not, but there is a link that you could read more about these different phases if you would like to. This nematic state, describing it, you can describe it kind of like pencils in a box. Okay, and imagine if the box is too big. You can shake them up so the pencils will still be oriented all kind of in the same way, but there might be a little bit of disorder and they can move within that box. Those are really sad pencils, but those are my pencils in my box. You have to imagine the box. Okay, so the IMFs hold them together in some semblance of order, okay, but there is some movement that can be made. Thermotropic liquid crystals. These are substances where this property is dependent only on temperature. These are pure substances. Let's contrast that to lyotropic, which is really a solution, and this phase is dependent on both the temperature and the concentration. Okay, so an example, we can have soap, the silk that's made from a spider. Those would both be examples of lyotropic liquid crystals. This is a particular structure that can form in these liquid crystals. These are called a micelle, and they're made up of the molecules. And this is one single molecule that would go into making this structure. If you look at this structure, we have a long hydrocarbon chain. Okay, this really would be your non-polar section. Okay, and I use that term loosely because it really is just the hydrophobic part of this liquid crystal. I didn't spell that right. Hydrophobic portion of this liquid crystal molecule, meaning it would not be attracted to water. This part would be the hydrophilic, meaning it would be attracted to water. In a high concentrated solution of these molecules, you will get the formation of these micelle structures. Okay, and this is a high concentration solution, and that would be an aqueous solution. Okay, so there's very few water molecules around, so the hydrophilic portion of the liquid crystal molecule is going to be attracted to the water molecules, but since there is such a high concentration of this, the nonpolar or the hydrophobic portion of the liquid crystal molecule is going to be attracted to itself. That's how I think about this structure. There is a link provided on Schoology that shows all kinds of these structures and some information on when they would form. I don't know if you need to know much more than this, but you're welcome to go and read up on other structures. Okay, so how do these liquid crystals work? If we're talking about really a phase of matter, when this molecule is a solid, the molecules have a regular arrangement and they have a regular orientation and they're locked in place. In a liquid crystal, the molecules have an irregular arrangement, but they are all oriented in the same way. So it's a regular orientation with an irregular arrangement. Heating this substance up further, we'd go into the liquid phase where the molecules have both an irregular arrangement and irregular orientation. It is this particular section here with this orientation that is regular and the ability to move that forms these liquid crystal structure. Okay, and those are thermotropic liquid crystals, and it's really a temperature range between solid and liquid, assuming that you have those other properties of the liquid crystal molecule. So when these substances are in their liquid crystal state, their properties vary with small changes in temperature, electric current, or a magnetic field. We can watch this YouTube video real quick. It's not this one, it's this one. And this is a liquid crystal paint that was placed on top of this copper sheet, and then they're going to heat it up by putting some electric current through it, and you can see the paint respond to it. This is the same type of molecule, I believe, that's used like in those mood rings, if you've ever seen those. Okay, so that's that. Okay, so these liquid crystal displays are used in watches, phones, TVs, computers, monitors, etc. A whole wide range of things. Important features: they are very low power usage and they can be backlit or they could reflect light. Okay, so here would be a liquid crystal display. These are chemically stable because they deal really with an alkane chain, an alkyl group, and these benzene rings. Okay, so this is really chemically stable due to the alkyl group and the benzene rings. And it is these benzene rings that give it the rod-like structure. Okay, they can exist as liquid crystals at appropriate temperatures. They are polar and they have a quick response time, meaning that they react quickly in an electric or a magnetic field. Okay, so polar meaning they can react to that electric field. And the quick response time means it reacts fast. Okay, so how do they work? They have a film of the liquid crystal substances used in the device. In the absence of a current, the liquid crystal is transparent and light can pass through it. In the presence of a current, the liquid crystal rotates. This blocks the light and it causes it to turn dark. Interestingly, there's different regions of the display can be controlled separately, and those allow for a range of images to be displayed. So the second part of this screencast is going to show the properties of molecules that are likely to show liquid crystal behavior, explain their liquid crystal behavior on a molecular level, describe and explain in molecular terms the workings of a twisted-nematic liquid crystal. This stuff's pretty cool. And describe the liquid crystal properties of Kevlar, explain its strength and its solubility in concentrated sulfuric acid. So at the end of the screencast, you should be able to answer questions on these different objectives. As mentioned quickly before, this alkyl chain, this is going to adjust the temperature range at which the compound exhibits liquid crystal properties. And the reason being is it is this group that makes the molecules less likely to be closely packed. And this lowers the melting point. So this is the group that you're going to adjust melting point of your substance to get it into that liquid crystal range. Okay. This biphenyl group, these two benzene rings together, gives the molecule its rigid rod-like shape. And then this nitrile group, or the functional group on the end of a liquid crystal molecule, in this case we're talking about biphenyl nitriles, so it's a nitrile group. This is the one that caused the molecule to be polar, which one increases the intermolecular attraction and it allows the crystal to be controlled by electric current. So it's this functional group that does the two functions. These tend to be stable because of the alkyl group chain being unreactive and the stability of the benzene rings. Okay, so Twisted-nematic LCD display, you need to understand a little bit about how this works. If I have unpolarized light, that's light that goes in waves in all different directions, and it's passed through a polarizing filter. If the second polarizing filter is oriented differently than the light coming through that small slit, you'll get no light on this other side. Contrast, if I have unpolarized light as a source going through this polarizing filter and the second polarizing filter is lined up, then you will get polarized light through the filter. So it's this type of idea that uses the Twisted-nematic LCD display uses in transferring light. Your liquid crystal molecules, when the switch is off, in between these two polarizing plates, lines up with IMFs, and it actually twists in its natural arrangement. The difference is on these plates there are small, there are small ridges. You can see them, the little lines that they have drawn here, that makes the molecule line up, and there's small ridges here that make it line up, so that this liquid crystal molecules kind of twist and held together by their IMFs when they don't have any current present. Okay, when I close the switch and voltage is allowed, the crystals will line up, and it no longer allows that light to kind of travel through those liquid crystal molecules. Okay, it shouldn't have light there. So let's watch a short video.
That would make me sad.
Today's modern LCD technology is based on a discovery made by engineers Lehmann and Reinhardt around 120 years ago.
Can we eat together like we like each other?
Let's take a look at the technology in detail.
Sounds like music.
In liquid crystals, the molecules are similar to long, drawn-out rods. As with crystalline structures, these molecules exhibit a strictly ordered crystal structure. The ordering of the molecules creates a directional orientation. In most LCD displays, the liquid crystals are embedded between two glass plates rotated by 90 degrees. This formation produces what is known as a Twisted-nematic LCD. A polarization filter is fitted onto each of the outer glass plates. These polarization filters mean that only one dispersion direction of multiple light waves emanating from a light source is allowed to pass through. The light follows the rotation of the molecules and, twisted by 90 degrees, hits the outer polarization filter. As the rotation means that the direction of the light matches that of the polarization filter, the light can also pass through this filter and brightens the outer glass plate at that point. If an electrical field is then generated between the glass plates, the special property of the liquid crystal molecule becomes fully apparent. As the molecules are dipolar, they react to the electrical field and are repelled. The rotated molecule structure is interrupted. When light then passes through the first polarization filter and follows the direction of the molecules, this hits the outer polarization filter and cannot pass through it. When a matrix is created from a number of these individual cells, it becomes possible to display graphics and images. To generate more colors, each pixel is divided into 3 subpixels. Color filters are placed over these subpixels in the colors of red, green, and blue. By triggering the subpixels differently, additive color mixing can be used to generate each color required.
Okay, Kevlar is a chemically inert solid. It's very strong and tough. It's used for bulletproof vests. And the question is, can we make it act like a liquid crystal? Well, if we look at the structure of Kevlar, we see that Kevlar has these benzene rings attached to a nitrogen, a hydrogen, carbon. So it's got the amide group, and it's got these hydrogen bonds between these molecules. And it's these strong hydrogen bonds and these alternating functional groups that lock the entire structure of Kevlar together and make it that strong substance. So what we need for a lyotropic is to have some regular arrangement, but also to break up some of these hydrogen bonds to make it to make those molecules somewhat mobile and able to move, to get reoriented in response to a electric field. So can we do that? Sure. So with concentrated sulfuric acid, this causes the C double bond O group and that NH group to become protonated, meaning they're going to have hydrogens attached to those. Okay? So this is going to break up some of that hydrogen bonding that holds those Kevlar molecules together so strongly to make that bulletproof material. Okay? And this results in molecules that are parallel but able to move, okay, kind of like logs down a river. Okay, so kind of like logs down a river. Okay, and the fact that this Kevlar has these benzene groups, rod-like structures, has a polar end and an alkyl group end. Gives us the features of the lyotropic molecule. So, at high concentrations, Kevlar does form a liquid crystal state. It doesn't have a real long alkyl group, but I guess these benzene rings give it enough of a structure. Okay. And that's the end of this screencast.